Hola guys, welcome back to my channel. So this is the continuation of the yesterday's question. So nuclear physics final exam question number 2. We are going to answer 2 out of 3 questions, but for the purpose of this video I will answer all of them. Okay, so without further ado, let's get started. So question A is to find the stable isobar. Okay, for the mass number of 77 using the liquid drop model. So as an introduction, liquid drop model is basically a formula or a model which is theorized that the atom of an element in periodic table that we always see is basically analogous to what we call a drop of liquid. Okay, for example, a drop of water or anything liquid. So if you observe that any liquid, for example water, so the force which holds the water or a liquid drop together is basically similar or analogous to the force which is the nuclear force holding the entire nucleus, which is consisting of neutron and also proton together. So because proton and proton is basically positively charges, so they are actually repelling with each other. So the force which held them together is basically nuclear force. Okay, the weak range of nuclear force. Okay, but in this case we need to find the stable isobar. You need to know what is the function of liquid drop model. So it is used to estimate, okay, to estimate the binding energy of the nucleus. All right, so binding energy is basically amount of energy needed to bind or to put the proton and neutron together inside the nucleus. So how much energy we need to bind them, okay, together. But it is also defined as how much energy needed to separate them, okay, to separate them away from each other so they are the same. Okay, so stable isobar, which means we need to find the maximum binding energy with respect to the proton number, which means we need to use the application of derivative. Okay, so first we list down the formula. So binding energy according to liquid drop model is, so AB, so this is the volume term times the atomic number minus surface term to the A to the power of 2 over 3 minus the Coulomb term Z square over A to the power of 1 over 3 minus A asymmetric term A minus 2Z square over A plus and minus delta. Okay, so delta is basically a pairing term, and then we need to find the d over dz, sorry, dBE over dz, which is maximized. Okay, hence this is actually means that the proton number is minimized. All right, so we need to, okay, because if you look at the binding energy formula or the liquid drop formula, when we take the derivative with respect to z, this volume term, okay, surface term, and also the pairing term will be 0 because it has no dependency on the proton number z. Alright, so dz, so we just left with, so minus AC z square over A to the power of 1/3 plus A asymmetry A minus 2Z square over A is 0. Okay, so let's take the derivative with respect to z. So 2z times AC over A to the power of 1/3 plus 2 times A asymmetry A minus 2Z over A times the derivative of the inner function, which is -2, is 0. So let's simplify. We can divide both sides by 2 basically, so this cancels. So we just left with -2, so I will move the -2 to the right hand side, so it becomes 2 A asymmetry A minus 2Z over A is AC, so Z AC over A to the power of 1/3. Okay, so let's distribute the term. So 2A asymmetry times A divided by A minus 4A asymmetry Z over A is Z AC over A to the power of 1/3. So let's make Z as the subject. 2A asymmetry times A, so divided by A is cancels like that. So let's make Z as the subject. So Z 4A asymmetry over A plus AC over A to the power of 1/3. Okay, which means Z is 2A asymmetry divided by the whole term 4A asymmetry over A plus AC A to the power of 1/3. So this is AC, right? Not 9. Okay, so because we are given that A is simply 77, A asymmetry is 23, A coulomb is 0.76, so all in the unit of mega electron volt. So Z minimum is 2A asymmetry is 23 divided by 4A asymmetry, 23 divided by 23 divided by A is 77, plus 0.76 divided by 77 to the power of 1/3. So this is how much? So let's plug in the value into my calculator. So I got 33.49. So we need to take the ceiling of the value, which is 34. So the ceiling, okay, which is 34. Okay, so the stable isobar has the Z equals to 34, A equals to 77, which means that the neutron number is Z minus A, which is 77 minus 34, 43. So if we have a atom with the symbol A, so like that, so we can label it as A is 77, Z is 34, then N neutron is 43. So this is the stable isobar of the atom, for example X. So if you look at the periodic table, you will see that the value of Z for the given A equals to 7, atomic number is 77, it is close to this value. So it is either 33, 34 or 35. So if you look at the periodic table, okay, you can check the value is close to this. Okay, alright, so next question is question 2. We need to calculate the binding energy of calcium 40 and calcium 41 using liquid drop model. So this is simple. So question B, so it is calcium 40. So if you remember, calcium has proton number 20, right? So the neutron number is 20 also. So calcium 41, so this is the isotope. Okay, so we need to find what is the binding energy. Again, the application of liquid drop model is used. Well, let me do not waste my time, just copy this formula that I've been written on. Okay, copy and paste it. Right. Okay. So the binding energy, first we did for calcium 40 first. So the volume term is given by 15.5, right? Is it? Yeah, 15.5. So let me look the formula. The constant value is 15.5. So I will substitute the value 15.5 times the A is 40 minus A surface 16.8, 42 over 3 minus the Coulomb term, 0.76 times Z is 20 square over 40, 1 over 3 minus the A asymmetric term, 23. So A minus 2Z is basically Z minus N. So it is 0 square. So this term will becomes all 0. So A is 40, doesn't matter. Plus and minus, so it's plus because the binding energy will increases because even nuclei. Okay, even nuclei, because the nuclei, which is the proton and neutron, has the even number. Okay, so the binding energy adds up or increases. So plus 11, so the delta is basically plus 11 plus 0 or minus 11. So in this case it's plus 11. Okay, so this term will cancels. So let's evaluate the value. .5 times 40 minus 16.8. Okay, 40 to the power of 2 over 3 minus 0.76 Z square, so 20 square, 40 to the power of 1/3 plus 11. So this is 345.62 mega electron volt. Okay, so this is calcium 40. So for calcium 41, the same thing. So binding energy will be 15.5 times 41 minus surface term 16.8, 41 to the power of 2/3 minus 0.76. Proton number is 20 also. So 20 square over 41 to the power of 1/3 plus or minus. So in this case is minus because, in this case is 0. Okay, because the value of the proton number is 20, which is even, but the neutron number is odd. So if we have even odd nuclei, so the delta or the pairing term is 0. So because the contribution of binding energy between the neutron and also proton cancels out. So this is 0. Okay. Oh yeah, don't forget the asymmetric term. So asymmetric term is 23 times with the difference in proton and neutron is only 1, so 1 square times with 41, which is the atomic number. So 15.5 times 41 minus 16.8, 41 to the power of 2/3 minus 0.76 times 20 square, 41 to the power of 1/3 minus 23 over 41. So we got approximately the same, equal, so 347.02 mega electron volt. So we see that the binding energy of calcium 41 is slightly greater than binding energy of calcium 40. So which means because the binding energy higher for the calcium 40, hence calcium 41 is slightly stable than calcium 41. So this is according to liquid drop model. Okay, according to liquid drop model. Okay, so question B done. So for C, so we need to find the total spin of the nucleus and the parity of the nucleon. So for the ground state of the following nuclei. So this is the application of shell model. Okay, shell model. Okay, so as you can see, I already paste the shell model. So this is actually shell model for nucleus, okay, or for the nuclei. Okay, so it is similar to the shell model of the electron, but this is a little bit deviated or a little bit different with the electron model. Okay, okay, so for the first element in question C is what? Let me see. So it is first beryllium 11, boron, carbon, and boron 12. Okay, so first one is beryllium 11. So beryllium, so oh my god, okay, beryllium 11. So beryllium has atomic number of 4 and neutron is 7. So this is the first element. Proton equals to 4. So the shell model is 1s 1/2 2. So this is not power, okay, so this is the number of proton in that S1s shell. Okay, and then 1 p3 over 2. So we need 2 more electron. So this is, sorry, not electron, proton. So 2 plus 2 is basically 4, right? So that's how it works. Okay, so that's for proton. Maybe I need to do it like this. Okay, okay, so neutron, okay, let me, neutron is equals to 7. So the shell model is 1s/2 2, 1 p3 4. So 4 plus 2 is 6. We need one more, 1 p12 1. Okay. So what is the parity of the proton? Okay, so this is because it is the S subshell. So if you still remember, our subshell is oops, let me use bright color, SPDF. So this is S is the angular momentum quantum number is L equals to 0. This is L equals to 1, L equals to 2, L equals to 3. Okay, SPDF. So for the P subshell, it is L equals to 1. So the formula for parity is, if you still remember parity, pi equals to minus 1 to the power of L. So if pi is positive, which means even parity. If negative, is odd parity. So L is 1. So this is minus 1 to the power of 1, which is odd parity. Or I can say pi is negative. Okay, pi is negative. For this also, pi is negative. For neutron, pi is negative. Okay, which is odd parity. Alright, odd parity. To find the because this is even odd, so even odd nuclei, because proton is even, neutron is odd, so the contribution of the spin, total spin, is from the neutron, because neutron is odd. So I is 1/2. Okay, so we just take the last quantum spin of the P subshell. Okay, 1/2. Alright, so 1/2 spin. Okay, so next one is boron 11. So boron 11, so 5 proton number and 6 neutron number. So let me copy down the proton, or Z is 5, neutron is 6. So using the shell model, so 5, so it's 1 S half 2, 1 P over 2 4, 3, so 3 plus 2 is 5. Okay, so same thing, 1 P over 2, so we need to take the maximum one, which is 4. 4 plus 2 is 6, right? So this is pi equals to negative, which is odd. Pi equals to negative, so pi is parity. Alright, parity. Negative. Okay, because it is P subshell. P subshell. Okay, so because Z and N is odd even nuclei, so we know that the contribution of the spin is from the Z itself. Okay, it's from the proton. So I total is, we just look at the last number of the spin state over there, which is 3/2. Okay, so that's the total spin. Next one is carbon 11. So this is the isotope of the carbon 12. Let's see. So carbon 11. So carbon Z is 6, neutron is 5. So it is similar, I guess, from the previous one. Okay, so let me copy down this, or just write it. Okay, doesn't matter. So it's 1 S half 2, 1 P 3/2 4. The pi is odd. 1 S half 2, 1 P 3/2 3. So pi is negative. Okay, And then the last one is the boron 12. Boron 12. So Z is 5. 1 S half, 2, 1 P 3 half, 3. Hence the pi is odd. For the neutron, oh sorry, I forgot to find the total spin state. Okay, let me shift this here. So the total spin state, because proton number Z and neutron number N is odd nuclei. So for this case, odd case, we need to use Northam rule. Okay, Northam rule. So Northam rule said that J1 plus J2 plus J2 plus L1 plus L2. So we need to find the parity of this. So J1 is basically for the first spin state, which is 3 half plus 3 half. So 3 half plus 3 half plus the angular momentum quantum number of each of them, which is in the p subshell, which is L equals to 1, right? So 1 plus 1. Okay, 3 half plus 3 half is actually 3. So 3, 4, 5. So see, 5 is odd. Okay. So odd. If the result is odd, then if odd, I will be J1 plus J2 simply. So it just adds up 3/2 plus 3/2, which is 3. So the spin is 3, the total spin state. Okay, then moving on, the next question is boron 12. So continue, the number of neutron is 7. So 1 S half, 2, 1 P 3/2, 4. We need one more, so one more is 1 P half 1. 1 P half 1. Okay, so 4 plus 2 is 6 plus 1 is 7. Okay, so the pi or the parity is negative because it is the p subshell. Okay, the p subshell, is it? Yep. Okay, so Z and N is odd nuclei. So we need to use Northam rule. Okay, Northam rule. So remember Northam rule. Okay, so this rule, okay, so this rule applies for the odd nuclei. So for the odd nuclei, we test to adds up the value of J1 plus J2, L1 plus L2, and to find the parity. So the J1 is basically 3 half. So this one plus that one plus L1 is 1 plus 1. Okay, so 3 plus 1 is 4 divided by 2 is 2 plus 1 plus 1, 4. So this is even. So if even, then I total is the modulus of J1 minus J2. So let's 3/2 minus 1 half is 1. Okay, so the spin total is 1. Okay, let me see. Yeah, I guess all good. Yeah, okay, let me check if I missed something in the question. Right, okay, all done. So yeah, so that's all for the second question of the nuclear physics final exam question. So until next time, and I hope there is no mistake. If there is, so you may comment in the comment section if there is a mistake or something I'm missing. Alright, so that's all. Thank you.